All right, 2.2 is going to still use a lot of the interval notation that we looked at, and I was able to retract my lead back to normal, so here we go. So increasing and decreasing. So what we're going to do is we're going to say a graph is increasing when a graph moves up as it moves from, I'm going to write it like this for shorthand, from left to right. And guess what that makes decreasing? And this is, maybe you've seen this in some other classes, but this literally is just a very shorthand way of saying repeat all the same words, but just change the word to down. So in other words, decreasing is when a graph moves down as it moves from left to right. And guess what? That does mean it is possible to not increase or decrease. The other thing is, these are, here's the key. I'm going to use a fancy word here. I'm going to say potentially subintervals of your domain. That's kind of the key idea here. Is what you're doing is you're saying from which place to the left to which place to the right am I moving up? From which place to the left to the right am I moving down? And so guess what? If we're asking in what section left to right are you moving up or down? If you say what section left to right, you're asking for a section of your domain because the domain is the part that moves left to right. So hopefully that makes sense there. And now let's look at these two quick examples. So A and B, and first thing to say is that these are functions. They pass the vertical line test, just to reiterate that idea. But look at A and B, and what we're going to ask ourselves is where from left to right. And that's the key here, is because I know there will be a later part in this course where we say this graph is moving up to the left and up to the right. But for now, we're going to instead turn ourselves like into a scanner printer, kind of like I mentioned on the last video. And we're just going to say, as I move from left to right, where's the graph moving down, and then where's it moving up? And so hopefully you can see that as we scan this graph, first, I'm not on the graph at all, or I don't see where I'm on the graph, but there is an arrow, so somewhere it's up here. But as I move from left to right, this graph in blue is decreasing. It is moving down until I get to a very special place right here. So I'm just gonna, I'm gonna draw a line here and then put a little exclamation point, or maybe 2 or 3 because that looked weird. So this is like the most important part of the graph here, because this is where something changes. So what we're gonna do is we're gonna say this graph was decreasing, and here was the subinterval that it was decreasing on. It was decreasing on, well, technically, as long as this graph goes left forever, it was decreasing. I only start to see it once I get here, but because it was doing this, it's decreasing that whole entire time from left to right, all the way until I get to 2. And notice that I'm putting an open circle, because even though this graph is like filled in here, where is it decreasing? Well, technically, since this is like, I'm just going to go ahead and call this a local minimum. That's going to help us later. But because this is a special minimum point, or this is the lowest point where it changed from decreasing to increasing, spoiler alert, then I can't say that 2 is solidly where it's decreasing, because it's a point of change. And then that brings us to increasing. Where am I increasing then? Well, here was the lowest point, and from here, now as I move from left to right, I'm now moving up on the graph. And so that would be from 2 to infinity. Now, what would make this really, really clear is, almost if we had like kind of an online graphing tool or aid, and we could grab this line and move it around, and literally if you took it from left to right, over here, it would be probably all the way up to like 180. And so then you're scanning and it's at 180, then it's at 90 because this is probably squaring, then it's at 45, then it's at 27, then it's at something, and then now it gets to the point where I can see it, but now it's at 3, now it's at 1, now it's at 3, now it's at 0, now it's at -1, and that's the moment where it stopped decreasing. But again, hopefully you follow that argument that like over here was probably all the way at like 150 or something like that. And then it's 75, then it's 35, then it's 20, then it's 15, then it's, as you can see, it's then getting down to -1, and then it starts moving up thereafter. Hopefully that makes sense. And with that being said, maybe you thought about this one. So what is this graph doing? Or where is this graph increasing or decreasing? Well, first, from negative infinity, or off the page, if I follow the trend of what that graph would do and think about what it would be all the way out over here, as I move from left to right, this graph is decreasing, actually, coincidentally, once again until I get to 2. So I'm going to maybe draw that line again, that this is a key point here, or a key place in the domain, because I was decreasing from negative infinity all the way to the left forever. It was moving down as it went from left to right until I got to 2, and then still always parentheses in this section. And then where am I increasing? Where does this graph move up as it moves from left to right? And the answer is nowhere. But guess what? I still haven't filled everything out on my domain, so there must be something else going on here. And there's a place of constancy where the graph does not increase or decrease, and that, in this case, is from 2 to infinity. From 2 on, the graph never moves up or moves down. It always stays -4. And that's what we mean by constancy. You always get the same y value. It never changes as you move from left to the right after you get to 2. All right, so hopefully not too bad. And hopefully you caught that what we did here is really we're splitting our domain into separate sections, if you can kind of see it that way. Now that brings us into this question, which would be a little more interesting to determine intervals of increasing or decreasing. But what we're going to do instead is we're going to look at what we call local minima and local maxima. Now those are your local lows and your local highs. Now what do we mean by that? Well, take a look at this graph. It is a function. It does pass the vertical line test, just to say that. And what I really want to do is I want to highlight, and again, it's these vertical lines that we're talking about in the vertical line test. As I scan, is there any special spots here like I identified up above? And the answer is yes. Here, here, and here. Those are my special 3 points. And maybe you can tell why. It's because where the graph at this point changes directions, that's what we call a local minimum right here, because it changed from decreasing to increasing, which means visually there's a low point. And a low point is what a mathematician calls a local minima. And why do we mean local? Well, because it might happen again later, or there might be something else going on over here. It's not the minimum for the entire graph, it's just a spot where there was a low point. And similarly, that would make this a local maximum. And so, what we're going to do is we're going to say local mins, catch this wording, occur at -4 and -2 and are -1. So what on earth do I mean by that? Well, let's list out the points on the graph right here, all the way back to the beginning. So if I were to draw out these points and describe what they look like, this first point, first going from left to right, is the point -4, -1. and the other point is -2, -1. And so notice what's going on here is we're saying the local mins occur at -4, -2. We're saying I plugged in -4, -2, and what it produced were the low values, -1. All right, so just catch that. They occur at -4, -2 because that's what you plug in to get them, but the value you get at the end is or will be -1. And so hopefully then we could describe our local max. We're not going to do all that extra writing. We're just going to say there's a local max at -3, and that local max is 3. So that's a local high point. Now notice that that's again referred to as a local high point because these arrows are saying you're going to go up forever. 3 is not the highest value you'll obtain. You'll actually obtain infinity. But at one point in time, there was a highest point or kind of a hill or the peak of a hill, and that peak happens at -3 for x, and the peak is 3 for y. All right. Up next, we dive into symmetries. Now, these symmetries are kind of the wackiest things to look at. But we're kind of just going to write it out here, is that a function's even if it has symmetry with respect to the y-axis, and we're going to say a function is odd if it has symmetry with respect to the origin. And so first, I just want to show you some visuals of what that would look like. In our notes, if you remember, we actually had that graph of absolute value of x minus 2. So maybe look back into your last section of notes for that one, but that would be an example. Let's say I had -x squared plus 9. I know you don't know what that graph looks like yet, but you will. Trust me that this graph has a peak at 9, somewhere up 9 if we scale that, and it then looks like this. And if I was a better artist or mathematician, then this graph would look completely symmetrical, and you could draw out a chart to see why it would be. But that's what this means to be even, or to have symmetry with respect to the y-axis. There it is. Now, what about an odd symmetry, or a symmetry with respect to the origin? What does that look like? Well, just to draw that picture, again, we have an xy axis, and we're not going to worry about the function that makes this, but as long as we write this down, this actually has symmetry with respect to the origin. Now maybe you can see what I mean by double flip, is that if I were to take this section and flip it over the y-axis and then flip that over the x-axis, it would end up being this spot exactly. And so that's what it means to flip over the origin. It means to flip over both axes and see if you get the same result. So again, notice what I did there, how I described it. I took this section, and what would it look like to flip it over here? After I do that, it would then look like this, which then I could flip again, and now I have what's on the bottom, and it goes the other way around. So if you can double flip, that's symmetry with respect to the origin. Now, there's another way you can write it, and this is kind of a wacky way, and it's this. Or in other words, and this is why we did this before, substituting a negative has no, I'm going to say, real effect. That's not a good word to use because real actually means something, but I think you'll know what I mean. Substituting a negative has no real effect on the algebra. That's what it means to be an even function. An odd function looks like this. this, again, is very, very abstract. But the idea here is, if I could write it this way, substituting a negative is equivalent to distributing, a negative to the whole function. All right, and that is what it means to be an odd function. If you replace this with a negative x, it's the same as essentially distributing a negative to the whole function itself. And I think we did that on another page. 1 minute, let me find it. It was in the last section. Like I said, we were kind of leading up to something. All right, so we can take a look at this function. Here is where we substituted a negative in place of x. Now, here's the way I can tell you that this is actually not even or odd, and let's show you why. Because when I plugged in the negative, all right, watch what happened. On the x squared, effectively nothing happened on that first term, but something did happen on the second term, and something didn't happen on the third term. So, in other words, when I substituted in that negative, did everything remain unchanged? No, something changed. And when I substituted the negative in, did everything change? No, only some things changed. And so that's why on that example we just looked at really quickly, that function was neither even nor odd. It was, well, like I said, neither, because plugging in the negative had some effect. It didn't cancel out completely. And plugging in the negative didn't equally affect everything. It didn't change everything and didn't fully distribute the negative. It only changed one of my three terms. All right, now there is a trick to even and odd for some of these what we call basic polynomials. There are some uglier functions that we'll look at later in the course that it's not as easy to notice this, but we want to know if these functions are even or odd. And I'm just going to actually spoil it and let you in on the secret. Look at these exponents. This exponent is an exponent of 5. This exponent is an exponent of 1. And guess what? The exponents, 5 and 1, are both odd. So what do you think this function's symmetry is? It's odd. Now what would be great is for extra practice to show the plugging in of the negative and showing that everything then negates. And maybe we'll do that underneath quickly, but I just wanted to really get to the spoiling of what the answer is. Now this one then, hey, take a look. There's an exponent of 6, there's an exponent of 2, and so 6 and 2 are both even numbers, so this one must be even. And you might be saying, whoa, Mr. Rao, wait a minute, what about this 19 over here? But the way you determine this for polynomials is not by the coefficients, the things in front of x, it's by the exponents, right? The numbers on top of x. So both odd, both even, then it's odd and even. And so take a look at C. What does that make C then? And it's tempting to say that C is odd, but C is neither. Sorry for the trick question. But here's why. It's because this right here, even though this is a 3 and this is a 1, this must be a 0 because I didn't see an x on this last term. And so that means there's an odd, and there's an even. It's mixed, and therefore it's neither. And hey, look, to call this back, that's why this one was the same thing. This was even, then it was odd, and we could stop right there and say, well, since I saw one of each, I know it can't be both. What I want to do real quick, just for extra, is I want to plug in a negative for A, talk about it, and show you why or what it means to be odd. So let's look at what that looks like for A. If I substitute a negative, and this is very abstract, what do I get? Well, let's work it out. And there's really nothing to work out, but there's a thought to have here. If you raise something to an odd power and it was negative, what would you get if you multiplied a negative together 5 times? And the answer is you would get a negative. And so this negative, because it's being raised to an odd power, would stay and transfer out. And I can just write it like so. So really, again, it's like I haven't evaluated it, but I'm more so saying, do I need to write this in parentheses? Will this negative remain after it's raised to the 5th power? And the answer is yes, so I can transfer that out in front. That's a really, really big abstract step there. And if you don't believe me, then by all means, try plugging in 2 and then plug in negative 2 and compare your results and kind of see where this comes from. From there, this would be negative 7x. And so, what is this? Well, this is actually equivalent to this. What do I mean by that? Well, look, I took the first term and the second term, both terms, and really it's as though I've just negated each one of those, which is this right here. And so, I've proven that when I did this, I got this. When I substituted a negative in, it was the same as distributing a negative to the original expression. That's what makes this odd. All right, I'll see you in the next one.